So that right there is the same as this right here. It is absolutely clear. I'm recording, Joe. Okie dokie, here we are. And no, it's okay, sweetheart. You can always talk. It's okay. I don't mind. It does the thing with diamonds where your finger looks like it's filling up the whole thing. And this is, I really don't know how much they weigh. They're more than my little scale can handle at 200 grams. It's more than 200 grams. And diamonds, when you shine a laser light up through them, like what I'm doing here, the carbon-14 inside the crystal lattice begins emitting electrons at that wavelength. Electrons are particles. They are things. They have mass. Not just photons are coming off of that because it has carbon-14 in it. Carbon-14 is the radioactive isotope of carbon. And all populations of carbon have a certain percentage of carbon-14 in them. And that is exactly why diamonds glow. Okay, they do. They glow. And when you have them in low light situations, you can see that they actually amplify the light that hits them. It jumps up one quanta of energy, except every atom in that stone is connected to every other atom in that stone through a double covalent bond. And that is why it transmits heat like a superconductor. Okay, if I hit the one side with something hot, the other side becomes that same temperature at basically the same time. That's how those little stupid diamond testers that people are so fond of work. And those little guys are designed for, I don't know if I have any small enough on maybe here. This is from Wish, and see those little guys there on the side? You can put the little connector on, the little tip of those diamond testers on there, and that stone instantly is the same temperature. And that's what they look for. That's what the heat test looks for in a diamond tester. Okay? Doesn't work on big diamonds because they're bigger than it's built for, right? If I had a much larger and hotter thing, I could touch it to this diamond and watch that heat be leached away by the structure of the diamond crystal. They're very, very reflective. What you are seeing, people say, well, you can't read through a a diamond. And they're right. It's because the light is being bent in by the structure of the stone. Okay? So we're looking down the z-axis there, and there are planes of cleavage that cross right there, right down the middle of that stone here to the little pointy part, right in the middle. And that way, the planes of cleavage are all lined up, hopefully the right way. When you line them up the right way, imagine if you put your hands out as if it were catching a ball or sunshine or something, both hands. The way those slope is the way we cut diamonds. So that one, the little pointy part, like this one, the rest of the stone, those planes of cleavage are heading up and out at about a 45-degree angle from the vertical here. So these triangles accentuate that. And it causes my clear diamond to have this darkness inside the stone. You see that? Light interfering with each other causes that darkness. And it has to do with the crystal structure of diamonds, not the cut of the diamond so much as the way we cut it. And the way we cut it is with those planes of cleavage catching the light. So we have several of these things to play with. 1, 2, 3, and I have a little tiny one, only about an inch, and I gave it away yesterday. Wouldn't you know it? I love giving diamonds away. Look at that. Because that's what diamonds do. That is exactly what diamonds do. And they are really, really tremendously beautiful. But they're not particularly rare at all. In fact, it's pretty much the other way around. They are ubiquitous. They are all over the place, and almost everybody calls them quartz. Because De Beers has convinced people that only those little tiny things that they sell at exorbitant prices are real diamonds. Well, they're wrong, because fault lines produce large, perfect diamonds, and they do it in great abundance. They're not rare at all. They are not rare at all. They're very, very beautiful. They're also very, very useful. See, this is from my mine over near Safford, Arizona. And when I first started finding these, I thought that maybe I had found a new red metal, because the stuff is so hard that it acts like a metal, except it's very, very light. It's lighter than aluminum. And because diamonds are held in a double, the atoms are held in a double covalent bond, it makes them stronger than steel times a bazillion. They don't melt, they wick away heat. They are the perfect building blocks for making spaceships. If I wanted to build a craft for multiple re-entries, that's what I would make it out of. Because on the way down, the leading edge will heat up, but it'll wick the heat away to the cold side, and you just fly through the atmosphere and it doesn't heat up. How about that? We're going to change the world, brothers and sisters, because diamonds are not rare at all. They're not. But they are useful as all get out, because I can make this red opaque diamond. And that's what this is. It's a diamond. This red opaque diamond, and I can make it. I can use it like one would use steel. You can mill it, machine it to very, very, very ultra fine tolerances to make miniature machines that never wear out. Never wear out. We can do that with diamonds. They are ubiquitous. I am finding them in gold and platinum, a gold-platinum alloy. And that's what you see there on the side of my little stone here. It's a little red diamond from the Gila River. It's a Gila River red industrial diamond. And boy. All right. You know what I need to do? See, what I've got here is like a really good diamond that I can carry around in my pocket, and doesn't hurt it at all. They don't get scratched. They don't. They do scratch though, so you don't want to put them where they're gonna hurt something else. But they do not themselves get hurt. Watch. Ha! I think I left a mark on there. Look at that. Now let's see if I can. Aha! There it is. You see those marks? 2 marks. The marks are the dust left behind from wearing off a little bit of the point of this diamond here. And this is a diamond. It's got really neat cubic structure, and you can kind of see that here. And it makes the tip of an octagon Look at that. See these four sides and this cool point, and that's the z-axis. You will always find a structure that looks like the corner of a box on a diamond, and there it is. Okay, and those are perpendicular to each other. They're three equal axes, and they are almost 90 degrees from each other. And that forms that box-like structure. It means that this is the upside, and when I turn it over, it's like those planes of cleavage, and they follow the lines of this crystal. Okay, so they're kind of leaning in against each other here. Some on this side, some on this side, and they crisscross each other, and that's what you see. That creates this four-sided symmetry in the termination. Perfectly flat. Perfectly flat. The thing about diamonds is they don't get scratched. They're very hard to break. And when you're cutting them, they're harder than any other mineral. The closest competitor is ruby and sapphire. And so putting a surface on, a good surface where the surface of the stone disappears, like this, is an art. It takes a long time to learn how to cut diamonds correctly. My diamond cutters in China know exactly how to do it. And together, we are going to change the world. Wishing you peace and prosperity ad infinitum.